Hello, Infinity. Hello, everyone. Come on in, ask questions if you have any. We've got about a minute before class starts, anyways. I'm so early. Anybody have any questions? All right. Need to check some. Everybody, I am in a state right now where I've got to figure out. I think our exams are technically scheduled for next week. So I have to make a decision as to whether I want to do the exams that week. I got to let my lab people know. So, for instance, if you're taking a lab other than with me, which most of you are, I have to make sure it's cool with them. But the main thing is it's supposed to be next week. And what night do y'all meet on lab?
Thursday night.
Thursday. Okay, that's not quite as bad as I expected. So at least she got over a week. So that's not a problem. I have one class that's my Monday class, but I think theirs is actually scheduled for the week after spring break, so that won't be a problem. So just pay close attention. I just made practice test 4 available, which covers chapters 5 and 6. If we take the actual next face-to-face test before the break, it will not cover chapter 6. I'm leaning towards going ahead and doing that, in which case I'm going to make another test that just goes up through chapter 5. So just pay attention to your email. I'll make the decision by tomorrow. So I just wanted to warn you guys with that. Now it's time to actually start. But I do want to ask again, does anybody have any questions on anything? I think I got you done since nobody's asked anything. I think I got you up to speed pretty well in chapter 5. There's one thing I didn't cover in chapter 5, and I wanted to cover that right quick, and that's basically the idea of drag and terminal velocity. So we have, studied, for instance, projectile motion where we were dealing with free fall. And in free fall, that means, of course, the only force acting on the particle is the force of gravity, which is manifests itself through the weight, which is m times g. Now, what I want to do is just imagine a falling ball of mass m, and imagine it having a velocity-related drag force. So the two drag forces that normally occur are either some constant times the velocity, and I use the word constant in air quotes there, or some constant times the velocity squared. So it's either a constant times velocity or a constant times velocity squared. There's a law called, I want to say it's Poiseuille's law or Poiseuille's law. I don't know anything about French, so I have no idea that I'm pronouncing that correctly. But the main thing is drag forces usually have some dependence on uh, in some sense how fast you're going. So for instance, it's not uncommon to think when I'm driving at 60, 70 miles per hour, that there's a high likelihood that the drag force is proportional to the square of the velocity. Whereas if I'm driving at lower velocities, I'm thinking it might be closer to just proportional to the velocity. Uh, if I'm doing so, let's say swimming underwater, I might think that that drag force is probably proportional to the square of the velocity as opposed to the proportional to the velocity. But in either case, it also depends on more or less the viscosity of the fluid through which it's traveling. So, for instance, if we're traveling in air, you can imagine the air doesn't make too terribly much of a difference, but it certainly makes some difference. You can tell that by, just a slow pitch softball, for instance. You can tell how much the air tweaks such a flight, even with the slow rotation of a slow pitch softball. I mean, you can see it do some crazy things when you cross the threads versus lie along the threads. That alone can show you quite a bit. So the viscosity takes into account not only the fact that air particles are sort of standing in place as a ball comes flying down, hits it, and it's got to knock these air particles out of the way. But in addition to that, some of the air particles don't get knocked away, they just get separated from their neighbors. So there's some ability of one molecule from air to be attracted to another molecule of air. And that is a little closer to the viscosity measurement. So that's an issue. Not only that, the cross-sectional area, which is really the area of the object that's falling, specifically that thing's area parallel to the ground. So if I fall or if I drop my hand in the air horizontal like this, then that area, in other words, how much pain it takes to cover that hand, is proportional and included in the constant that goes in front of the v or the v squared. That is a relevant factor. So falling this way has a air resistance that's proportional to this area, whereas if I fell this way, then it only has a air resistance proportional to this little area. Okay, so that's something else to take into account. Hopefully you guys are following that. Yeah, does everybody understand what I'm saying there? All right, so let's get started by, check this out. You're going to be very impressed. I'm going to share my screen. I crack me up. I'm the funniest person I know. All right, so I'm going to share my screen and I'm going to imagine a wee little ball falling to the Earth. And it actually doesn't have to be the Earth. In fact, it can be pretty much any planet. The main thing is we're going to have a force of gravity that is mass times gravitational acceleration. And we're going to have a force that, in this case, I'm choosing to do a B times V. So what we'll imagine is a little ball right here, has a mass M. It has a force acting on it. That force is mg. But there also happens to be a force acting in the upward direction, and that force is actually not constant. I'm going to say that force is the drag force, and it is the force proportional to the velocity. So what that means is the faster the object starts to go, the bigger the force is. And eventually what happens is you'd expect, since the velocity is still going up, even though there is a drag force, you expect the drag force to be going up. And eventually what will happen is the drag force will get so big that it's equal in magnitude to the mg. And when that happens, it should stop accelerating. And that's the concept of terminal velocity. So what I'm going to do is I'm going to imagine this is my positive y-axis pointing downward. And I'm going to take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. But this time, A is not a constant. Okay, so it's fine using m times a when a is a constant, but in this case, we're going to see when I put the forces in, let me do that now, mg minus bv is equal to m. You can see the fact that the mg is a constant is good. That could suggest the acceleration is a constant. But the fact that the b times v is not a constant means the acceleration is not going to be a constant. And instead of a, I'm going to write this as dv dt. Because remember, a is equal to dv dt. Of course, I could also have written d2x over dt squared, but that wouldn't help me because you see on the left-hand side of this equation is a result that relates to v. So if I had used d2x over dt squared, I'd have a problem, and I have to actually call that v dx dt. And then it's a whole different differential equation. So we're going to stick with this as it is right now. But the first thing I'm going to do is I'm going to multiply both sides by 1 over m. And when I do that, I get g minus b over m times v is equal to dv dt. Another person just came in. Now, what I'm going to do as well is I am going to multiply both sides of this equation by dt. Okay. And then I'm going to multiply both sides of this equation. Well, actually, I'll do that step first and go from there. So when I multiply this, what I'm going to get, make sure, oh, no, another person came in. When I multiply both sides by dt, I'm going to get g minus b over m v times dt is equal to dv. All of this has a parenthesis around it. So now what I'm going to do is divide both sides by g minus b over m v and divide this by g minus b over m times v like that. And when I do that, I'm just going to get dt on the left-hand side is equal to dv on the right-hand side over g minus b over mv like that. That's going to show me that I do in fact have what we call a differential equation. And in fact, if you take the differential equations, this will probably be the very first equation you solve like on the first day of class. So don't fret it too much if you don't get it right now. Hopefully me showing it to you will make you feel a little bit better and a little more confident going into differential equations, but it shouldn't be too terribly hard. And hopefully the more of these you see me do, the more likely you'll be to not have a problem in your class. So I'm going to integrate both sides, and it's important, of course, that you integrate both sides from the same place. So I'm going to say from t equals 0 to some t later. Normally, a mathematician would want me to write like t prime or make the variable of integration t prime or something, but we just run with it as physicists. So in this case, on the right-hand side, we're going to integrate from v0 equals 0. So I'm specifically going on the assumption that we drop this thing from rest, and that's going to be integrated up to the function v of t. Now, that is not necessarily that straightforward, but there's a very simple substitution we can do. I'm going to say let u equal g minus b over m times v, then du is equal to negative b over m dv. Okay. So when I do that, what I need is a negative b over m in front of the dv. So I could put a negative b over m right there. And to make that okay, I can do it to the other side as well. Okay. So by multiplying it by both sides, that makes it okay. And I'm not doing anything like, randomly multiplying by a factor on one side but not the other. So now I can take and integrate both sides. Clearly the integral of dt is just t. So I'm going to get, I'm going to get negative b over m t, because once you evaluate the integral of dt, you get t, and then you take it at t equals t, you get t, and you take it at t equals 0, you get 0. So it'll be negative b over m parentheses t minus 0, right? There's no need for me to write the t minus 0, so that's what I'm showing you here. Now, on the right-hand side, the negative b over m is in fact du. So now I can just realize that this part right here is just equal to the integral of du over u. And I think everybody knows that that is the natural log of u. Well, the natural log of u means the natural log of g minus b over m times v. And of course, I've got to evaluate that from v0, which is equal to 0, to v of t. So in this case, I get negative b over m t is equal to the natural log of g minus b over m v of t. I'll put that in square brackets since I've got a parenthesis inside of there. Now I'm going to say minus the natural log of g, because what I just did was I substituted v equals 0 for v, and that gave me just g there. Now I can use this to say negative b over mt is equal to the natural log of g minus b over mv, all that divided by g. And that's just from the property of logarithms that says log a minus log b is equal to log a over b. Okay, does that make sense how I got that? I noticed this gave some of my students a problem earlier. They weren't quite piecing it together. So I just wanted to make sure y'all knew that. Now, what we're going to do is I am going to assume that I can raise e to the left-hand side power and set that equal to me raising the e to the power of the right-hand side. So what I'm really doing is I'm imagining putting a lowercase e down here and here. And of course, e raised to the ln power is just the argument of the ln. So now I get, and I'm going to write the t on the other side, by the way. Now I get g minus b over mv of t. I didn't write v of t over there because I didn't have room. All that would be over g. There's something cruddy and sticky on my screen there. That's the right-hand side. The left-hand side is going to be negative b over mt like that. Now I'm going to multiply both sides by g. I'll get g minus b over mv of t is equal to g e to the negative b over mt like that. Now I'm going to bring the GE to that side and bring the negative B over M to that side. When I do that, I get G minus G e to the negative B over M t is equal to B over M V of t. So now what I'm going to do is multiply both sides by m over b. And I'll factor out a g on that left-hand side too. So I'm going to say this becomes mg over b times 1, oops, let me give myself a little bit more room there, times 1 minus e to the negative b over mt is equal to v of t. That's the entire expression for the velocity as a function of time. Now, if we look at F equals ma, I want you to note if the summation of forces in the y direction is equal to 0, then m-a-y, which is equal to m dv dt, is also equal to 0. Therefore, you get mg minus bv is equal to 0, which means v, which equals v terminal, is equal to mg over b. Okay, so that's what we get just thinking about the physics of Newton's second law of motion. we find out that there is a terminal velocity. And just from a force standpoint, with regards to Newton's second law, that velocity should be mg over b. And what terminal velocity means is that the speed is going to stop increasing eventually. And when it does, it's going to maintain that constant speed. Well, that constant speed is mg over b. Now, of course, all bets are off if you do stuff to change B. And remember, I said B might have the or should have the viscosity of the fluid that you're flying through, but it also had the cross-sectional area. So if I'm falling, plummeting from the aircraft to my death, okay, if I lay out to try to belly flop, then my cross-sectional area, the area parallel to the surface of the earth, is going to be quite large. And in fact, if I wear one of those squirrel skydiving suits, it even has like flaps down in between the armpits so I can get the area even larger. That would be a good technique to try to prevent dying when I hit the ground from falling from an airplane. Of course, that also brings into the thing is that, well, Billy, you're going to have to crush the poop out of your face and you're going to have to land face first, which is not all that awesome. But if I wanted to actually speed up, maybe I'm jumping out of the aircraft to go chase some villain because, I'm clearly, obviously, like a Mission Impossible kind of guy. So I'll jump out of the vehicle, the aircraft, and I want to rapidly catch up to that dude who's already jumped out with his parachute. So what I do is dive head first because then my cross-sectional area is just sort of the shadow I would cast if the light was directly overhead, which is a itty bitty shadow, right? So I do that and I'll go really, really fast and I'll catch up to them. And then hopefully I can do whatever I need to do, like in whatever movie. All right. So if you actually made a plot of this, we would hope that this velocity as a function of time would reproduce what our ideas of the terminal velocity is. And we think our idea of the terminal velocity is that the terminal velocity is mg over b. So when I actually go to graph this as a function of time, I can put a velocity here on the vertical axis, and I can put time right here. And what I'm going to say is, let's call this quantity mg over b. If you plug in t equals 0, you get 1 minus e to the 0 power. And anything other than 0 raised to the 0 power is 0. So that means t equals 0 corresponds to velocity equals 0. Now, if you look at this, you'd say, okay, well, this looks like a exponential of some sort, but what it really is a constant minus an exponential decay, which means it's essentially like a exponential growth being added to a constant. And in fact, what you find out is that this line right here is an asymptote. And that's what the velocity as a function of time looks like. You can use Desmos or whatever if you want to graph that and see that it actually works out that way. And in fact, you'll find basically for time periods of m over b, you'll have like a 38% approaching of the terminal velocity. Okay. I'll also make another note. Let's do this one. The units of b should, of course, be equal to newtons times seconds, per meter. Because if you notice, when you have mg minus bv, they're supposed to be able to be added. So the bv has to have units of newtons. And that means the b must have units of newtons divided by meters per second. And a newton divided by a meter per second is the same thing as a newton second per meter. So that's part of it. And I'd also say that b includes viscosity and cross-sectional area. Okay. So that's basically it. If I ask you any questions, they'll mostly be, stuff about plotting this. If I actually do give you this, I'd have to give you the b value, or I could ask you to solve for the b value, but have to give you everything else, that kind of stuff. So the two main things you need to know is that the terminal velocity is mg over b. I've got that boxed off, and that the final velocity is that. You don't need to be able to solve this differential equation. Okay, that's beyond the scope of this course, but hopefully after taking me for 2 semesters, you should have seen enough to where you feel a little more comfortable with dealing with differential equations. Anybody have any questions on that? All right. Well, that completes all of chapter 5. I will be pushing the chapter 5 homework to be due this Sunday, as opposed to the actual concepts were due last night. I think for everybody they were due last night, but the actual questions were supposed to be due tonight. I'm going to move all that to Sunday. Okay, so don't worry about that. Also, those of you who came in late, I mentioned that I will know tomorrow whether I'm planning on going ahead and having your midterm, your second face-to-face test before we go on break or after we go on break. I'm going to try to make that decision tonight or tomorrow and let you guys know via email. So just keep your eye on that. I did already make practice test 4, which is chapter 5 and 6, and that would be an online test, and that definitely is not happening or not due until after the break. But that practice test is already available. If I have the next face-to-face test, if I have it before the break, it's only going to cover chapters 1 through 5. If I have it after the break, it will include 6 as well. Okay. Any questions? Everybody follow everything we did there? All right. So this brings us to chapter 6, which is gravitation and Newton's synthesis, is what they call that. So if you actually think back to the little discussion we had. I know I didn't cover as much of it in this one as I did in my face-to-face class, but around the time of the life of Galileo and Kepler, they were contemporaries, as well as Brahe. He was a contemporary of them as well. Copernicus was a little older, but still, I think I'm pretty confident he was still alive, or maybe, no, that's right. That's right. He had died. So yeah, because Copernicus actually didn't publish his work until he was literally on his deathbed for obvious reasons. But anyways, what we had was a model of the solar system that was really a model of the universe. Because in this time period, about 400 years ago, basically the universe to those people was the sun, the moon, uh, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and then the stars. And the stars that we see with the naked eye are all within on the order of 1,000 light years away, not much more than that. So if you'd imagine a sphere centered on us, whose radius is on the order of 1 to 10,000 light years, something around there, then that would be the universe of the ancients. In the early 1900s, we actually built the 100-inch telescope, Mount Palomar. I think it was Palomar. And anyways, that's where Hubble was. And Hubble was the first person to measure what was then called the Andromeda Nebula. And nebula just sort of means a cloudy area of the sky. They didn't necessarily know what it was, but once you get a 100-inch telescope looking at it, you can start to see what it is. It is an island of stars. And ultimately, we've now determined that that is in fact another galaxy, and it's 2.5 million light years away from us. At the time, he was using a wonderful result that one of our female astronomers, what Edward Pickering referred to as his calculators, one of those female astronomers had come up with this really brilliant idea. Specifically, she noticed that there were certain types of stars that varied in brightness. So if you watch them over a week or 2 weeks or 4 weeks, you'll see that the brightness goes up and then comes back down and then goes up and then comes back down. We now understand that what's going on with that star and why it does this. But at the time, They were called Cepheid variables because they were like a star in the constellation Cepheus. And she realized that there was a relationship between how much light they put out, which is called the luminosity, versus uh, their period of oscillation between brightnesses. So once you figure out, whether the period is 1 week or 3.5 days or whatever, from that you can tell exactly how much radiation is being put out by that star. And the brightness that we see here is just the luminosity, which I was just talking about, so total radiation put out, divided by 4 pi times the distance away squared. So if you know the luminosity and you know the brightness, which we can always measure the brightness because it's just counting photons landing on our film here or on our chips here or whatever, you can then use that to find the distance. So she had come up with this wonderful, and I'm sorry, every time I do this, I don't know why, but I never come up with her name. Anyways, I should. It's a loser. It's a really bad thing that I did this. But anyways, uh, she had come up with this very early on, and the data we had wasn't that great. So when he applied that same formula to a Cepheid variable that he saw in the Andromeda galaxy, he came up with it being on the order of 100,000 light years away, which wasn't that big, but it was way bigger than anybody thought. So it was amazing. And it was big enough that he realized, hey, this is a whole nother island of stars. We might even be a part of an island of stars. And in fact, there's probably a lot of other islands of stars. And then ultimately, Hubble did look for all those different nebulas, and various nebulas actually turned out to be galaxies. Other ones just turned out to be what we still call nebulas, which are birthplaces of stars. They're little cloudy, gassy, dusty areas. But what he discovered was that if you find a galaxy that's, let's say, 100 million light years away, that thing is going to be running away from us at, let's say, 100 meters per second. I'm just making up these numbers, by the way. Okay, there's a whole different set of numbers. But anyways, if you found a galaxy 100 million light years away and you found that it was going 100 meters per second flying away from you, then what Hubble showed was if you find another galaxy that's 200 million light years away, guess what? That one's going to be running away from us at 200 meters per second. And if you find one at 300 million light years away, that one's going to be flying away from us at 300 meters per second. So, in other words, the distance is directly proportional to the velocity. The only way we can explain that, by the way, is a Big Bang that created not only all the matter in the universe, but the space itself. It's got to be the space itself. So that's kind of crazy, but that's what we ultimately got in the early 1900s. And prior to that, like I said, we had that sphere of stars of radius, maybe 10,000 light years across or something like that. That's about all we knew of. And we had a system of epicycles and deferents that explained all that. So, for instance, there was this neat thing that happened when you look in the night sky from one night to the next, you pretty much see the same things. Like if you go out tonight, you could see Orion. And Orion looks like, 3 little belt stars and then a foot star and another foot star and then an armpit star and another armpit star and a couple little stars and a bow and stuff like that. And if you come back an hour later, it'll still look like that, but it'll have moved up and maybe towards the south a little bit. And if you come back the next year at the same time, it'll look exactly the same way. However, if you come back about 6 months from now, you won't be able to find Orion anywhere. So all of those shapes were almost like they were painted on the inside of a sphere that was rotating around us. And that's where we got the idea of us being the center of the universe. But the ancient Greeks noticed that not everything followed those simple patterns. So, what normally happens is you look to the east and you'll see a star low on the horizon. And if you come back an hour later, that star, at least here where we are, will have gone up and to the right. And if you come back a little later, it'll have gone up and to the right again. And in fact, it goes up and to the right, up and to the right, up and to the right until it gets due south of us. Then it starts going down and to the right, down and to the right, down and to the right until it disappears. all stars seem to be doing that, but there was these things that the ancient Greeks called basically wanderers, and the Greek word for wanderer is planetos. So they named these ones that sort of wandered through constellations. They literally would come through like this. Like you look in Gemini, which sort of looks like a star, 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 and then a mirror, star, star, star. And you'd see a new star there that you hadn't seen before. And if you wait, it'll do a little loop de loo. And even that, when it does the loop de loo, it gets really bright when it's going backwards and then it goes back forward again. So they had to explain that. So they ultimately made a crazy system where they had the Earth at the center. Then there was an imaginary line from the center of the Earth to the center of the sun. The moon orbited all through that line, didn't pay any attention to that, and was very close to the Earth. But then between the Earth and the sun, there was a orbit, and then on that orbit, which we called a deferent, on that orbit was an epicycle, another itty bitty circle. But in the case of Mercury, that itty bitty circle's center stayed on that stupid line that connected Mercury and, or excuse me, that connected the Earth and the sun. And Venus exhibited the same sort of behavior. So it had an epicycle and deferent that it wobbled around as well. And the center of the epicycle had to stay on that little line too. And that was because both Mercury and Venus never deviate very far from the sun. Venus does farther. I think it's like 47 degrees is the farthest Venus will get from the sun, and Mercury might be like 32 degrees or something like that. So that's the only way they could explain it, is just this imaginary line. They didn't have any reason for it, but it was there. They were using Aristotelian physics, which said the heavens were perfect and couldn't change. And since they can't change, that means things can't slow down or speed up. Everything in space, and since the heavens had to be perfect shapes, and therefore the perfect shape was the sphere or maybe the circle. So all this crazy stuff was tied up into it. Now, in addition to that, it wasn't just Mercury and Venus that did those loop-de-loos. The other ones did too. So outside of the orbit of the sun around the Earth, there was another episode, or excuse me, another deferent for instance, Mars. But Mars will run right through one of those constellations and do a loop. So they put an epicycle on it, and the epicycle, not only did it show or make sense of why it made a loop, but the fact that the epicycle allowed it to get closer to the Earth when it was going backwards was also a salient point, because that said, hey, not only have we explained why it goes in a loop, we've also explained why it gets brighter when it's going backwards in that loop. So that was the model of the solar system that we had when Copernicus comes along. So Copernicus, the Polish astronomer and member of the church, is one of the astrologers, which that was sort of a science to them back then. And such astrologers would make part of their living by predicting where the planets will be for 5, 6, 7, 10 years in the future, so that people that ran cities and states and countries and stuff like that could actually predict exactly when they needed to do things. For instance, some holidays are based on, for instance, the moon. Some holidays are based on the summer solstice versus the winter solstice versus the vernal equinox and all that good stuff. And then they also had astrology, which again they didn't have the scientific revolution yet, so they didn't realize that astrology was a pseudoscience. So it really paid them to know, hey, where's my birth constellation if I'm the ruler of this nation? All right, where's the birth constellation of this woman that I'm thinking about marrying and making my queen? Those types of decisions had to be made. So that's what astrologers like Copernicus and Galileo and Tycho Brahe would do. Uh, well, Copernicus had had enough of it, and by the time Copernicus gets a hold of it, there's something like 80 some circles within circles within circles. There's equant points and deferents and all sorts of crazy stuff. And in fact, Kepler said in a letter, I want to say it was a letter to Galileo, he said, had I been around when God created the universe, I would have asked him to make it a little less complicated, right? So it's just really a mess. Well, Copernicus was kind of sick of it and said, I think we've lost our way from what Aristotle taught us. And therefore, he saw a much more simpler design by taking the Earth from the center and pulling the sun there. And then the sun would have Mercury orbiting at its closest, and that exactly explained the shortest period of rotation, or excuse me, period of revolution for Mercury. And then Venus was second farthest, and therefore had the second longest period, or second shortest period. And then Earth, and then Mars, and then Jupiter, and then Saturn, and that was it. Okay, that was really nice, but the reason for Copernicus doing that was sort of the antithesis of the scientific revolution. Specifically, he was saying, hey, Aristotle taught us a lot of things and we've deviated from that. Not, hey, the evidence is showing us something better. Therefore we should jump ship and try that new better thing. No, he said, we still got to stick to Aristotle. And in fact, we're going to have circular orbits and the planets can't speed up or slow down. Well, Kepler comes along. He has his own ideas of what the universe is made up of. He thinks it has something to do with the perfect solids being the exact number of perfect solids is exactly the number of perfect solids you would need to separate the sun from Mercury, Mercury from Venus, Venus from Earth, Earth from Mars, Mars from Jupiter, and Jupiter from Saturn. He figured that can't be a coincidence. So he starts making up his own model, sends it around. Tycho Brahe reads it and like, this guy's a really good mathematician. So he hires him and Kepler comes there. Brahe's got his own model. Now, Brahe doesn't have a nose. He got it cut off in a sword fight over who the best mathematician was. So he would actually stick this gold and silver nose to his face with wax. And you could imagine what kind of sight that would be. And he was, plus, he was somewhat royal. So he had very high estimates of himself and he wouldn't let himself look like lesser of a person. So he ended up partying all day so much that his bladder exploded and he became septic and died. Really a horrible case. But Brahe had a model that was completely different in the sense that he had the sun with Mercury orbiting it. And then outside of that was Venus orbiting the sun. And then outside of that was not Earth, but Mars orbiting the sun. And then Jupiter and then Saturn. But check this out, that whole thing was orbiting the Earth. That was Brahe's model. Kepler gets there. He's not given data as quickly as he wants, but Brahe dies. He goes to court, wins the right to finish his work and get Brahe's data against the well wishes of the family, or excuse me, against the wishes of the family. And he works out that Brahe's model doesn't work. He works out that his own model doesn't work. He works out that Copernicus's model does not work. And ultimately, he comes up with an entirely new system, and it's called Kepler's laws of planetary motion. And the weird thing is, he's got no reason for believing these laws work other than the fact that it fits the data. So he doesn't have a physical argument for why these laws are the case, but lo and behold, they turn out to be the case for all systems. Okay, so that does leave us with understanding why that the planets are doing certain things, and it makes the calculations of where they'll be in the future a lot easier. But it still doesn't tell us why are they doing that. That was the job of Newton. So if you look, for instance, at our Earth, let's say our Earth looks like this. Yes, I'm using the feature of my drawing program. So there's the Earth. And let's say this distance right here is the Earth radius, which we'll call R with a circle with a plus sign in it. That's the astronomy symbol that we tend to use for the radius of the Earth or for the symbol for the Earth. Now, some distance away, that means I'm skipping quite a bit of distance. Some distance away will be the moon, and the moon is about a quarter of the size of the Earth, like so. And in fact, this distance from here to here is in fact 60 Earth radii, and Newton knows it. Okay. Well, Newton had been studying light, and one of the things we know about light is if you have, for instance, just a little light bulb, a point source, if you're 1 meter away from that light source, the light's pretty bright. If you move instead 2 meters away, it turns out that the brightness of the light drops not by a factor of 2, but by a factor of 2 squared, which is 4. That's called a 1 over r squared law. Newton knew that. And he's looking at this, and the way he tells it is he's been sent home for the plague from Cambridge. He's sitting out in his mother's apple orchard. He looks up at the moon in the sky and realizes how the moon and the apples on the tree are very similar. So he says, I wonder if the force that's pulling this apple to the ground when it gets so juicy that the stem can't hold it anymore, I wonder if that's the same force that's causing the moon to change its direction, because Newton's first law of motion says an object in motion tends to stay in that state of motion unless acted upon by a net force. So something has to be causing the moon to move. He said, well, if it is, then I wonder if it's a 1 over r squared force, because what he knows is at 1 Earth radius, the acceleration is equal to 9.80 meters per second per second. And he says, well, since the acceleration due to that force is 9.8 at 1 Earth radius, if I assume that the moon's acceleration would be the same thing, but it's related by 1 over r squared law, then he'd expect the acceleration at 60 Earth radii would in fact be 9.80 meters per second divided by not 60, just like I said, not the light didn't get dimmer by a factor of 2, it got dimmer by a factor of 2 squared, which is 4. Well, this is going to get dimmer, or this is going to be less accelerated by a factor of not 60, but 60 squared, which is 3,600. And lo and behold, that number turns out to be 0.00272. And of course, it's in meters per second per second. Now, we've learned in chapter 5 that centripetal acceleration required to keep something in a circle of a constant velocity is v squared over r. And we know that the velocity for the moon would have to be about 2 pi times the radius of the Earth times 60, because that's how far away it is, right? So the circumference divided by the period is the velocity. So I'm going to take the circumference, which is 2 pi times 60 times the Earth radius, which is 6.38 times 10 to the 6 meters. And now I'm going to divide that by around 30 days. And of course, 1 day is equal to 86,400 seconds. And then all that is the velocity. So we're going to have to square that. And then we're going to have to divide it by the radius of the orbit, which again is 60 times 6.38 times 10 to the 6 meters. Well, when he did this calculation, he got 0.0027222, so on and so forth, meters per second per second. At that instant, Newton is the only person on planet Earth that understands why the moon orbits the Earth, why Venus and Mercury and Earth orbit the sun, why Mars orbits the sun, and even Galileo had made this observation by now, even why the satellites of Jupiter, Io, Europa, Ganymede, and Callisto, they all orbit as well. Newton understands it, and he then goes forward and is able to use his law of gravity, which he introduced as this. What Newton said was there is a universal law of gravitation. The force of attraction between two bodies that have a mass m is a constant g times the mass of one of them times the mass of the other one divided by the square of the distance between them. If these objects are actually not point particles, then technically speaking, it has to be something like this, where this is M1 and this right here is the center of mass of M1. That little X mark there is the center of mass. This blob over here could be M2, and this part right here might be the center of mass of that one. If that's the case, then the force acts right along that line, and in fact, the R in the formula is exactly that distance R. Okay? So we see the force of attraction is thumbs up with one of the masses. That's because F is in the numerator and M1's on the opposite side of the equals with the numerator. F and M2 is also thumbs up. And then F and R is thumbs up, thumbs down. Okay, that's because F and R are on opposite sides of the equal sign, but they're also on opposite sides of the fraction bar because you can write F over 1. So what that means is if I double mass 1, I double the force. If I triple mass 2, I triple the force. If I do both, if I double mass 1 and triple mass 2, then I increase the force by a factor of 2 times 3, which is 6. Taking that a little further, if I increase the distance, let's say from 100 meters to 2 meters, the distance went up, so the force should go down, but the force is not going to go down by 2. It's going to go down by 2 squared, which is 4. And if I triple it, it'll go down by 9. If I quadruple it, it'll go down by 16. If I quintuple it, 25. If I sextuple it, it'll be 36, so on and so forth. So that's sort of the concepts behind this that you're supposed to know. So the key things that you get is that formula right there gives you the magnitude of the gravitational force. And it's called a universal law of gravity because it's going to act, well, one of the reasons is because it's going to act as a force of attraction between two objects, period. Long as they have mass, they're going to have a gravitational attraction. Now, your book does this. It calculates the gravitational attraction between two humans that are close together, and you get like 1/1,000,000th of a Newton, which is like a very small amount, basically. Okay, so way less than a pound, almost non-detectable. So gravity is really, really weak. Now, the other thing he's telling you is, yes, this is it, but also notice that there's no value of R you can put in that equation that gives you F equals 0. Can anybody think of an R I could put in F equals G M1 M2 over R squared to get a 0? So you see, really the only way you could possibly do it is you take the limit as R approaches infinity. And that literally means the force of gravitational attraction reaches across the entire universe. So that's another reason why it's called the universal law of gravitation. So yes, he gives us the magnitude. He tells us that the force will be parallel to that line. So for instance, if we wanted to know the force on 2 due to 1, it would be that. If we wanted to know the force on 1 due to 2, it would be that. Okay? So you have to be able to do this. You have to be able to calculate a magnitude and then figure out what line along which it lies so that you can compute, for instance, an X component and a Y component. Okay, so that's part you're going to have to do. I'm going to do more of this next week, so don't worry too much. That's why I said if we have our exam next week, this is not going to be on it. But for instance, if we had a mass right here and another mass right here and another mass right here, if this was an equilateral triangle, then we know this is 60 degrees, this is 60 degrees. And what you'd say is obviously, what's the force on this one? Well, that force would be along this line. Let's call this one 1. Let's call this one 2. Let's call this one 3. So this would be F3 equals question mark. This would be the force on 3 due to 1. Notice it acts right along that line. This, of course, would be 30 degrees. So once we calculate the magnitude, let's say the magnitude of F31 is equal to 256.7 newtons, then we would say F31 sub, let's say sub Y, where I'm going to say this is my x-axis, this is my y-axis. I'm going to say that F31 sub Y would be this little part right here, and the x would be that little guy right there. So what I would do is I'd take the 256.78 newtons and multiply it by the cosine of 30 degrees, and I'd put a negative on there. Okay, that's because it's pointing down and my y-axis is pointing up. Similarly, I would say F31x, that also points to the left, which is a negative x direction. So I'd put a negative there, 256.78 newtons times, in this case, it's going to be the sine of 30 degrees. So that's how you would make that particular force a vector. Of course, you could do the same thing over here. This one would be F32, meaning the force on 3 due to 2. This would have a slightly different x component and a slightly different y component if, of course, the masses were different. And F32, the magnitude of it would be G times M3 M2 over R32 squared. And by the way, when we did the experimental analysis to find out G turned out to be 0.0000000000667 and some units, which turns out to be 6.67 times 10 to the negative 11th. And that unit is a Newton meter squared per kilogram squared. Okay. So that formula right there in red using that purple G, that's how you would calculate the 256.78 that I just wrote. I just made that number up just to give you an idea what the magnitude would be. So in this case, the F32, let's say the x component is going to be, in this case, it's a positive, and it's going to be, let's say when I did this calculation, I got 500.0 newtons. Then in this case, it'd be 500.0 newtons times the sine of 30 degrees. And then the F32y would be, in this case, it's still negative. So I'll put a negative there, and I'd say 500.0 newtons times the cosine of 30 degrees. So does everybody have an idea how you would make a formula G M1 M2 over R squared into vectors? Y'all see how that plays out? Because this is a pretty straightforward thing to do. I think y'all are up for it. But at the same time, I just wanted to give you some example of that. Now, you'll notice there's some extra credit. I think it was in week 6. I'm going to move it to week 7, which is what y'all are in now. Things like calculating the gravitational force, or actually the gravitational acceleration at the top of Mount Everest, and then at the bottom of the Marianas Trench. So you'd have to Google how high Mount Everest is and have to Google how deep the Marianas Trench is, and then calculate how G changes. That's one case. For that, by the way, what we've already decided is weight is equal to mg. But now that we know the law of gravity, we also know that that weight is g times the mass of the object falling times the mass of the earth. And the only time mg works like that, m lowercase g works like that, is when we're fairly close to the surface of the earth. And when I say fairly close, like I mean the distance from the surface of the earth is way less than even a tenth or 100th of a% of the radius of the earth. So this part down here is just going to be the radius of the earth squared. Now, if you look at that, you can see that this m and this m cancels out, and that shows you that gravitational acceleration, the 9.8 that we know, that should be g times the mass of the earth divided by the radius of the earth squared. And it even works out to meters per second per second. Any questions on that part? So when I say you can calculate the G at the top of Mount Everest, what you're going to be doing is, instead of using the radius of the Earth down there, you're going to take the radius of the Earth, which is 6.38 times 10 to the 6, and you're going to add 29,035 feet. Of course, you got to convert that to meters, but that's the height of Mount Everest, is 29,035 feet. If you read Into Thin Air, you'll know something close to that. It's actually changed by quite a bit since that book was written. You'll have to Google the deepest part of the ocean, which is probably some part of the Marianas Trench. And then in that case, you're going to do the radius of the Earth minus that number. And that'll give you G at Mount Everest and G at the bottom of the Marianas Trench. Any questions on that part? All right. So this is a hodgepodge of everything you need to know to be able to do chapter 5. Next time, I'm going to actually work some examples, more of them. But what I need to do now is Kepler's laws of planetary motion. So Kepler goes into this looking at all these different scenarios. And to Brahe's credit and to Kepler's credit, Brahe and Kepler don't necessarily get along that much. They're very different people. They're sort of like Ned Flanders from The Simpsons. That's how Kepler acts. He is, super straight laced, super conservative, super religious, at no chicanery, no funny stuff, work all the time. The only time he takes off work is when he's going to try to fight for his mother to keep from being burned at the stake as a witch because she ain't got any teeth. Uh, all sorts of terrible things like that. Meanwhile, Tycho Brahe's like a party animal. So he's like Seth Rogen or Russell Brand, who used to be married to Katy Perry, or some crazy person like that. So just imagine the most crazy Ozzy Osbourne type of character you can, and that's sort of Tycho Brahe. He, not only did he party all day and stuff like that, he had a pet human that we would nowadays call a little person. So literally, he treated them like, like they were a pet. He once got a deer so drunk that it fell down the stairs of his castle and broke its neck and died. So he just was not, he was kind of reprehensible in many ways, or at least from a modern perspective. Okay. So these two guys not getting along is not that cool. But still, when it came down to it, and Kepler was trying to say, hey, do I trust Brahe's data, or do I trust that Brahe's data is bad enough where I can say Copernicus's law is close enough? He throws out Copernicus's law and trusts Brahe's data. And Brahe didn't have a telescope. He literally just had like a protractor mounted into the wall with very precise measurements etched out on it. Okay. So that's really pretty impressive what Brahe had as well as what Kepler had. So let me get to Kepler's laws. So Kepler's laws of planetary motion. Oops. Evidently, the A comes after the T. Now, remember, this is a prescriptive formula that tells you how you can predict where the planets will be, but it doesn't tell you why, right? He's just using the observations that he has to come up with some explanation that he can use to calculate things. So his first law is the planets orbit the sun in elliptical. And he said elliptical. He didn't say oval. Elliptical has a very specific mathematical meaning. If you remember from pre-calculus, it was, x squared over a squared minus b squared minus y squared over b squared is equal to 1. That's what he means by elliptical. Okay. So the planets orbit the sun in elliptical orbits with the sun at one focus. So that needs a little bit of explanation. You probably all know that if you put a nail into a piece of plywood and then you tie a string to that nail and then you tie a pencil to the other end of that string, if you pull the string taut and work really hard to keep that pencil upright and keep that string taut, you can trace out a circle. Okay, that's how you make a circle. If you want to make an ellipse, you do sort of the same thing, except what you do is you put 2 nails in the plywood. Okay, now these nails represent the focal points or foci, F-O-C-I, of the ellipse. Okay, but now what you're going to do is you're going to take a string and you're going to make sure it's longer than the distance between the nails. And you're going to tie it to one nail and then tie the other end to the other nail. And then you're going to put your pencil in there and pull it taut like that. That description, in fact, can be used to derive the elliptical equation. But when you do this and you keep that actual rope taut, it traces out a shape sort of like that, where this distance right here is called your major axis. And this distance right here is called your minor axis. Okay. And in fact, I'm trying to nail this right here down the center. This distance from here to here is called your semi-major axis. Okay. And that semi-major axis is in fact what we call A. Okay. Now, if you think about this being the sun, then you'll see this distance is the closest the planet will get. And this distance is the farthest the planet will get. Okay. What is the name of that red line, which notice goes all the way to the middle of the nail, plus that purple line? What's the name of that length? Can anybody see from my diagram? So I'm saying go from add up that little red line that starts on the far left-hand side of the orbit and ends at the middle of the left nail, and then that purple line that starts at the middle of the left nail and goes to the right end of the orbit. What is that total distance?
Your diameter?
It is, but I gave it a
Oh,
very specific name. Look at the drawing. Is it my writing that you can't read?
oh, would that be the major axis?
Exactly. So that is equal to the major axis. But notice that red one is the shortest distance, and that purple one is the largest distance. So if you wanted to have an idea of roughly what the average distance between the planet and the sun is, would it be reasonable to take the average of those two? The shortest distance and the longest distance? Yeah. So what is red plus purple? Oops. I tried to spell purple with a B. What is red plus purple divided by 2, which is actually equal to the average distance? Can y'all tell me what that is in terms of anything I've drawn on my picture?
Would that then be the semi-major axis?
Exactly. So one of the things we do to make sure you guys know everything is we will say, what is the average distance between uh, the planet Mercury and the sun? And all we'll give you is the period of the planet Mercury. So when you hear that word average, you think, oh, he's talking about semi-major axis. So he wants me to calculate semi-major axis. When you see Kepler's third law, you'll know why that's relevant. Okay. All right, so that's enough of what we have right now. There's other details. There's something called the eccentricity. As the eccentricity approaches 0, it becomes a circle. As the eccentricity approaches 1, it becomes infinitely thin and, in fact, a straight line. So that's really what it is. I'll also tell you that Pluto actually has the most elliptical orbit. And if I were to draw an exact replica of Pluto's orbit on the board, and then draw an exact circle about the same size right next to it and not tell you which one's which, you would not be able to look at them and tell which one's the circle and which one's the ellipse. You'd have to do some measurements to do it. So I hope you can have some appreciation for how brilliant Kepler was to figure out that that was exactly an ellipse. Isn't that cool? All right, so that's Kepler's first law. Kepler's second law is the planets sweep out equal areas in equal time. Okay. What does that mean? Well, let me draw an ellipse real quick, or my attempt at an ellipse real quick. Okay. So let's say that's an ellipse. Looks decent, not great, but decent. And let's say our sun is right here. Okay. So if a planet goes from right here to right here, and we call this area A, and in fact, it took 30 days to do that. If we were to make another shape with the same area, obviously it's a lot longer to the other side of the orbit, so it's going to have to be a lot narrower. So I am going to draw this little shape right there, and I'm going to say that area is also A. That means the planet went from here to here in 30 days. So you can see clearly the planet went faster on the left than it did on the right. Does everybody see how that works? Okay, so that is two things that smack Aristotle and Copernicus in the face. One, the orbits are bastardized circles. That's an ellipse is like the ugly little sister of of a circle, or the ugly little brother of a circle. So that's kind of bad. Two, the planets are actually speeding up when they're closer to the sun and slowing down when they're further from the sun. So that's completely different from what Aristotle suggested about the immutable heavens, which means they're not supposed to change. Clearly, they did. So Newton's able to prove all three of these, by the way, with his law of gravity immediately thereafter, and he even goes so far as to say there's no way any force can ever create a closed orbit unless it's a F equals kx force, meaning force is directly proportional to x, like for a spring, or a F is equal to some number over r squared force, which is what gravity is. Those are the only ones that can create closed orbits, and Newton's able to show that. Let's go to number 3 now. By the way, this Kepler's second law is consistent with the idea of notice how the planet is closer to the sun on the left and it goes faster, and then it's farther from the sun on the right and it goes slower. Though this has nothing to do with this particular thing I'm getting ready to say, it's still consistent with it. So if you want to know which one's faster, Mercury or Venus, you just say, well, Mercury's closer to the sun, just like the left-hand side. So I could use that to remember that Mercury actually has a faster orbital speed than Venus does. Okay. So even though the second law has nothing to do with that, it's not speaking to that at all. It's a nice mnemonic to help you. So hopefully you guys will get that. Uh, the last thing he found was that the square of the period, whoa, of the planets, or let's say a planet's orbit is proportional to the cube of its semi-major axis. So that means t squared is proportional to a cubed. If you forget that, what you can remember is where do we sell, or where do you see on television people celebrating January 1st, the new year? Anyone? It's just a mnemonic I'm helping you with. There's a lot of different places they do, but one of them's pretty famous.
Times Square.
Yep. And notice the period is a unit of time and it's squared. Okay. Now, that is Kepler's 3 laws of planetary motion. And in fact, y'all can give this a try yourself, but if you set G M of the sun over R squared, if you set that equal to M velocity of the planet squared over R, you can see immediately that the m's cancel out. And in this case, I'm pretending like it's a circular orbit. Okay, that's why it's mv squared over r. In reality, you'd have to deal with some of the other stuff if you wanted to take this into consideration. But the main thing is now you can see that also one of these r's is going to cancel out with that. And now I have G times the mass of the sun divided by the orbital distance r, which is supposed to be a constant since it's circular. Well, that's equal to 2 pi times the orbital distance. Remember, velocity is for a circle is circumference divided by period. So I'm going to say that is the period there and square it. And now I'm going to replace the r's with a's so that it looks more like that. When I do that, I get ultimately t, whoa, Nelly. Dang it, come on. I get t squared by putting the t over there is equal to 4 pi squared over g times the mass of the sun times a cubed. So that is a quick and dirty derivation of Kepler's third law. Any questions on that? All right, so I've given you enough details where you can solve any problem from chapter 6, to be honest with you. There's some more stuff that I would like to show you examples of, but you can definitely get started on this. Our time is up. You guys are free to go. Please send me a chat real quick with your first and last name in it so I can use that for a roll. It looks like most of you already did it. Maybe all of you did. I'm not sure. If you hadn't, please do that before you leave. I'll wait for the last person to go. I am going to push chapter 5 homework to be due Sunday as opposed to tomorrow. I did mention that, but I want to remind you guys. And also pay attention to your email so you can find out about the next face-to-face exam. Thanks for coming, everybody.
Thanks. Have a good night.
You too, Jennifer. Thank you. Diego, did you have a question? All right. He's gone. All right. Bye, everybody.